Hello students, welcome back. Let us resume our discussion in section 5. Previously, we went through the idea of Riemann integrability. Here's a sketch. We established the underestimation and overestimation using the minimum and maximum as function values, which we call lower Riemann sum and upper Riemann sums, as you can see from these illustrations. Lower Riemann sums touch the graph from the below, so underestimation. Upper Riemann sums touch the graph from above, so it's an overestimation. Put those together in the same viewing window, we're going to get something like this. Blue is overestimation, upper Riemann sum, and pink is lower Riemann sum, the underestimation. Arbitrary Riemann sum will be captured somewhere in between. So we have two worst behaving terrible cases. Terrible overestimation and terrible underestimations. How do they behave? It turns out lower Riemann sums increase. No. Here, lower Riemann sums increase and upper Riemann sums decrease. We have increasing limit, which we called lower integral, and we have decreasing limit, which we call upper integral. And these are bigger, so the limit rule stays, the bigger quantity stays bigger, so limit of bigger quantity stays bigger, and limit of smaller quantity stays smaller. So lower integral is less than or equal to the upper integral. Now, when do they become equal is the question, and when they become equal, then the common quantity is called the Riemann integral, and we say the function is Riemann integrable. In this case, every Riemann sum will be squeezed in between, and they will all converge to the same quantity. You see, every Riemann sum will be squeezed in between if you take the limit somewhere in between, but this one and that one are the same, so they all go to the same quantity, which we call Riemann integral. That's what we established so far. But then again, all those are, okay for definition, but in practice, how can you apply all those? Well, that's why we have to consider the fundamental theorem of calculus. It turns out, if f is continuous, then no problem. It is Riemann integrable. So, f is a continuous real function in a closed bounded interval, then the lower integral and upper integral are the same. So it is Riemann integrable. And then f is antidifferentiable. In other words, there's an antiderivative function. Finally, using the antiderivative, we can calculate the definite integral. It turns out the definite integral, or Riemann integral, is a net change of the antiderivative. We have been using only the third part so far, but as a matter of fact, the fundamental theorem of calculus consists of these three parts. The first is the hardest. But we're going to take a bit of a shortcut, and I'll try to explain as much as possible in the first part. And the second one, I'll probably end up skipping. And the third one is actually easy. Now, how does this thing work? Here's a sketch. We take upper minus lower. So upper integral minus lower integral. We subtract this smaller quantity from bigger quantity, so the difference is, of course, non-negative. Now, compare this upper integral with upper sum, and upper sum is greater. You see, upper sums get smaller, smaller, smaller as we take the refinement, and this decreasing limit is the upper integral, so upper Riemann sum is bigger. Same thing goes for lower Riemann sum. Lower sums increase as you get finer, so it gets bigger, 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 and the increasing limit is lower integral. So this one is smaller. Even bigger minus even smaller, so this quantity is certainly bigger than this integral minus integral. And then we're going to overestimate it still further. What is the upper Riemann sum? It's a Riemann sum like this, except that we have maximum here. Lower sum is this one, except that we have minimum here. Okay, all right, same partition, same delta x size, minimum here, maximum there, maximum minus minimum. We put together as maximum minus minimum. And let's consider this quantity, maximum minus minimum. It looks pretty big, but we have to consider we're going to do very, very thin rectangle, very small interval for continuous function. Is there a good illustration? I think I can show you something here. Okay, here, this is not very good. I prefer the next picture. Okay, this one here. If we have a continuous function, then minimum is there, maximum is there. Looks like we have a substantial difference. But as a matter of fact, that's because this subinterval is really wide. If the interval gets really thin, we're going to consider this kind of picture. So let's take really thin rectangle like this. And then what's the difference between maximum and minimum? Very, very small, you see. Let's take a little bit thicker rectangle. Still, maximum minus minimum, that's very small. See? Maximum minus minimum, that's very small. Now, if I do that in a region with discontinuity, maximum here minus minimum, that can be really substantial. That's because there's a discontinuity. But when we have just a continuous function, maximum minus minimum, that's really small. And it's going to get smaller, 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 and going down to zero if the interval width go down to zero. Does it make sense? That's what we can do. So maximum minus minimum will become so small, it will be bounded by something that's going down to zero. And yes, that's going down to zero. Consequently, this quantity is greater than or equal to zero, but less than or equal to zero. Yeah, it's equal to zero. So they're the same. So lower integral and upper integral are the same. It's not a precise proof. Actually, I skipped the uniform continuity part, but otherwise, everything is pretty much there. So, continuous function is Riemann integrable. Does it help for part 2? Yes. Because Riemann integral exists, you can define your antiderivative function using Riemann integral. You can define it like this. Remember, you can do it finally because this expression on the right-hand side is valid. F is continuous, so integral exists, so we can define a function like this. And then from here, doing this Newton quotient computation is a bit of an ordeal, but it turns out okay if you calculate Riemann, this Newton quotient. Capital F of x plus h, so we have integral up to x plus h, and we have integral up to x. Subtract from the other, Then we have integral from x to x plus h. So we are talking about very, very thin interval again. So the illustration is kind of like this. So we have a graph of a certain function. And then we have, pretty thin interval like this. Basically, this is x, and that's x plus h. So that this interval width is h, which is getting very small. So this f of x here, or f of t rather, anywhere here is not too different from f of x here. This one right here. Anything here, f of t, that's pretty much same as f of x. So I can replace this f of x by f of t here by f of x, which is a constant, and then take it out. Then with integral of 1, and then x to x plus h, and then divided by h. If you do your computation, it'll become just 1. So you have just f of x times 1, and that's precisely what you want. The Newton quotient will go to small f of x. So the derivative of this capital F function will become small f of x. The detailed integral computation is a bit tedious, so I'll leave you there. But the main idea is replacing this f of t by f of x because the difference is meager. Here in this notebook, I wrote it in really formal fashion, so it looks really intimidating, but it doesn't have to be this bad actually. And then finally, once we have 1 and 2, 3 is actually easy because capital F of x, a2x, f of t dt, then capital f of b is a to b, f of t dt, and capital F of a is a to a, f of t dt, and that's 0. So yes, we have the integral written as antiderivative function, capital F of b minus capital F of a. So we have the fundamental theorem. When we have a continuous function, we can always calculate this integral using the antiderivative computation. But not only that, the hardest part, as a matter of fact, is number 1, the integral exists, and number 2, antiderivative exists. You see, the existence part is always the hardest. Okay, we still have a couple of exercises, and these examples are lower and upper integral computation. In this case, my function value is 0 when x is irrational, 1 when x is rational, and this kind of thing, you cannot even draw the graph. It's whatever you do, it's invalid. There are uncountable many zeros out there, and then infinite many ones out there. How are you going to draw that? It's impossible. But you can still calculate lower and upper Riemann integral, kind of like this. In any interval, there got to be some rational numbers, irrational numbers there. So the minimum is always 0. So out of all zeros, you're going to get 0. So lower Riemann integral is 0. Upper Riemann integral, on the other hand, in whatever interval, we have some rational numbers there. So maximum is always 1. So 1 times delta x is delta x. So you're just adding up all those widths of the subinterval. So we end up with the width of the larger interval b minus a. So these four difference. So we have a function that is not Riemann integrable. As for the last problem, I'll just show you the graph and then we'll just leave it there. Does it make sense?